Now what we are going to do is that we are going to examine the question of convergence of this improper integral. Now here in this case, the antiderivative of this would be a problem. So what we can do is that we can just play around with some similar function that we can compare this integral with. So for example, if we remove this 2 here and look at x over e to the x, then what we have is that this antiderivative is, let me just rewrite it here too. So this is the same as the antiderivative of x times e to the negative x, and if we use integration by parts, then this integral would be negative e to the negative x times x plus 1. Now if we took this integral or an improper integral using x over e to the x, namely this one with the same limits, then just taking the limits and using L'Hopital's rule here, what we will get is that we will get that this integral equals how much? 1. Okay, so, or this improper integral converges to 1. So what we have is this now, that is, notice that this function here, it's a non-negative function, and at the same time it is dominated by this function, right? So now graphically, this black graph is that of x times e to the negative x, or x over e to the x, and this magenta graph is that of x times 2 plus e to the x to the negative 1, or x over e to the x over 2 plus e to the x. So what we saw is this, or what we know is that here the area between the x-axis and the black graph, namely this improper integral, it converges to 1, and this magenta graph stays below. Actually right here they are the same, but otherwise it's below the graph of below the black graph. So what we can conclude here is that this will converge as well. Okay, so we decided the question of convergence, and then if you want to see the limit that it converges to, sometimes you may not be able to get the exact value as here, but you can make approximations, as I'm going to show you, by using this graphing calculator by Desmos. Okay, so when you pull up this window, I have just enlarged the calculator area and reduced the graphing area here. And if we go for show keyboard, go to functions, and if that doesn't show up, for example, you see this, just click on miscellaneous, so integral sign will show up, and here you may say, okay, we want to take, say, the integral from 0 to 10 of the function that we were looking at. Okay, what was the function here? So this, then the value turns out to be 0.7178738. All right, and we can just go on taking the larger and larger integrals until we see the values stabilizing. Okay, so here in this case we have 7 up to this place. It has stabilized up to 7, 3 is the same, but so let's proceed further and see. So here what we have, I'm just stammering, I'm sorry, 71787, 7183. So this is becoming larger, and of course this will go on becoming larger. So let's see this here. I just brought this value back, and I'm changing the upper limit to 30, just being lazy for typing. So what has happened now, it has become the same digits up to this. I'm not talking about rounding. Okay, so if we do this, Okay, so then let's see, we have 834, 834. Here we have 39, here we have 42. All right, and well, let's go up to 50 and see what it does in comparison to the previous one. Now these two values have become identical, and in this case you can see that just this keeps on monotonically increasing this improper integral as you let the right hand side go further. But however, here you can see it has stabilized at this value, right? So what we notice is this then, that this integral is approximately this value, or if you have something like this scientific notebook that I'm using, you can find an approximate value, and here it's going like further down. So up to here you can see the values match. All right, so let me know if you have any further questions. Okay.